For scalar numbers, our four basic functions are addition, subtraction, multiplication, and division. So far for matrices, we understand how to add and multiply. For scalars, we can understand subtraction as adding the negative. For example, 6 minus 3 is 6 plus negative 3. We can similarly understand subtraction for matrices. A minus B can be written as A plus negative 1 times B. And since we understand scalar multiplication, here by negative 1 on B, and addition of matrices, we can understand how to subtract matrices. In a similar vein, we can also understand division of scalar numbers as multiplying by the inverse. For example, 6 divided by 3 is equal to 6 times 1 over 3, the inverse of 3. For a number a, the inverse of that number, written as a to the negative 1 power, is defined so that a to the negative 1 times a is equal to 1, as well as a times a inverse. We will use this idea to define the inverse of a matrix, but instead of the number 1, we will use the identity matrix I. Similar to our notion above, for an n by n matrix A, the inverse of a matrix, written as A upper negative 1, is defined as A inverse times A equal to the identity matrix I is equal to A times A inverse. Recall that for scalar numbers, we can take the inverse of any number except 0. In the context of matrices, there will be many matrices that do not have an inverse. We will call a matrix that does have an inverse invertible or non-singular, and call a matrix without an inverse either non-invertible or singular. We will use these two pairs of terms interchangeably. Since some matrices are invertible and some are not, it will be helpful to have a way of determining this. To do this, we will define something called the determinant of a matrix. The determinant of a matrix, written as det of A, gives us a way of telling whether or not a matrix is invertible. The determinant of a matrix is defined for any n by n matrix, though for our course we will restrict our study to 2 by 2 matrices. The determinant of the matrix can be found computationally as det of A, B, C, D equals A times D minus B times C. That is, as the product of the values on the diagonal, A times D, minus the product of the value on the off diagonal, B times C. Now, there is a lot of important theory about the determinant, many of which you'd learn in a linear algebra course. However, for our course of study, the result that will be most important is that the determinant of A is not equal to 0 if and only if A is invertible. So this gives us a quick way to determine if a matrix is invertible or not, by computing the determinant and checking whether or not it's equal to 0. Let's look at an example. Here, let's compute the determinant of the matrix 2, 1, 6, negative 3. To find this, we will take the product of the diagonal, 2 times negative 3, and subtract the product of the off diagonal, 1 times 6, giving 2 times negative 3, which is negative 6, minus 1 times 6, which is 6, and negative 6 minus 6 is negative 12. So we've found that the determinant of 2, 1, 6, negative 3 is equal to negative 12. Therefore, we could conclude that this matrix is invertible, since the determinant is not equal to 0.